Amazing. Hello, hello. We are so delighted to see you all. I am so honored that we have a very special guest and teacher today, teaching the first of three classes this year. And we have Dr. Paul Daley here, and Paul Daley worked with Sasha in the lab from 2007 until Alexander Shulgin passed in 2014. And Paul continues to manage the lab here at the Shulgin Farm and Foundation. And yeah, he continues to pursue the discovery of new compounds. So I am so excited to introduce Dr. Paul Daley. Over to
Well,
you,
and
Paul.
greetings. It's a real honor to have such a big crowd and from such far-flung places. So yeah, I'll give a quick introduction. I met Dr. Shulgin in 1977 when I was just starting my PhD work at UC Berkeley. Um, I've got kind of a lifelong interest in psychedelics, but since I started my college career right on the heels of the passage of the Controlled Substances Act, when interest in psychedelics was considered professional suicide in many scientific circles, I ended up kind of taking my uh, passion for environmental protection to heart and got my degrees in environmental toxicology and entomology, worked in plant protection and environmental physiology for a few years, and then got drawn into environmental chemistry at a large national laboratory where I worked for 30 years here in the just outside the Bay Area. But I did, as Stacy pointed out, started visiting with Sasha in the early 2000s, and there was just a need. It seemed to have someone who both had a love for the technical side of his work, and also who was willing to put up with the cobwebs and the kind of funky nature of the lab. And this is, and I'm speaking from the Shulgin lab right now, not a fake background. So, what I thought I'd do today to open up this series of talks is uh, give a broad and hopefully not too shallow introduction to the phenethylamines, which were the class of psychedelics that Sasha made his greatest original contributions in. These are the compounds that are related to mescaline, but there are a number of other structures that have very interesting and hopefully useful properties that people are getting excited about in medical and psychiatric use now. And so with that, why don't we dive into it? I'm going to share my screen, so you're not going to be seeing me, but uh, my presentation here. Stacy, you can fill me in. Am I displaying that okay?
You sure are.
Great. So I just need to do this. And I think we're ready to go. Okay. So as I said, I'm Paul Daley, and I will say that if anyone has like pressing questions during the talk, please go ahead and fire them off. Sometimes trying to hold on to an idea for more than 20 seconds is something I can't do. So, feel free to jump in. Okay, so what are phenethylamines? This is a little sort of dictionary quote that I pulled from the beginning of PCAL, which I presume many of you are probably aware of. This was sort of a semi-autobiographical book that Sasha and his wife Anne wrote in 1991. It's acronymic. PCAL is phenethylamines I have known and loved. And here we go. The word phenethylamine uh, comes from references to gases of all things, but put together they describe a compound that's naturally occurring both in animals and plants. It's a compound that's in all our brains right this instant, but it also refers to any of a large series of compounds that take the basic structure of phenethylamine and modify it to various ends. So here we go. They're numerically the largest class of known psychedelic compounds. They're also some of the oldest known, both to indigenous peoples here in the Western Hemisphere and to scientists broadly speaking in Europe and the United States. Uh, Chemists often refer to a basic scaffold, a kind of a core structure common to a class of compounds. And in this case, phenethylamine consists of a six-membered aromatic ring. Uh, Taken alone, that would be a benzene ring, but incorporated into other structures, chemists refer to this as a phenyl group. So we have a phenyl group, a two-carbon linking chain, ethyl being the name for that. You probably remember from chemistry, methyl, ethyl, propyl. So ethyl refers to a two-carbon chain. And then the amine refers to the ammonia-like group that are on the right. Um, in organic chemistry in particular, the functional group that kind of confers the chemical behavior of a molecule is often used to name the whole structure. So this is a primary amine with that ammonia-like group. For instance, if you were to drop some phenethylamine into a neutral water solution, it would start to have a basic pH reaction. So one of the naming conventions that we run into is you name the carbons that go away from that functional group with Greek letters. So you'll notice the little alpha and beta in the ethyl chain. Uh, Sometimes these compounds are referred to as the beta phenethylamines. So that just refers to the phenyl group being attached to the beta carbon away from the amine group. So I thought I'd spend a second, since I've got a large group here. I have no idea how much chemistry any of you have had. I talked briefly about how we draw these things. There's kind of a hieroglyphic um, style that organic chemists use to kind of illustrate the structures that we're talking about. And fortunately, in organic chemistry, we're only dealing with a handful of different elements. So by and large, carbon, hydrogen, oxygen, sometimes nitrogen, sometimes sulfur and phosphorus are really the sum total of all the elements that we're dealing with. Um, Makes it a lot easier than inorganic chemistry. We've got that whole darn periodic table to deal with and all those electronic orbitals, and it's just a big bunch of trouble. So anyway, we're only talking about a few different kinds of atoms, but they can be joined together in astonishingly complicated ways. So what we do as a shorthand is to illustrate how the atoms are attached to one another. Uh, uh, we can have a complete shorthand which would just list the elements that make up a given molecule. So in the middle of the plot here, I didn't mean to do that. In the middle of the plot, I have C8H11N. That's called an empirical formula. It tells you what elements are in a given molecule, but they don't tell you anything about how they're arranged. So uh, in the bottom, I'll give you kind of a conceit that we use. We will draw structures where the elements, the atoms, are joined with lines. Each line indicates an electron pair that's shared between those two atoms. And in organic chemistry, we pay attention to the number of bonds that different types of atoms want to have satisfied in order to have a neutral structure, one that doesn't have a charge, either positive or negative, indicating a loss or gain of extra unshared electrons. So in the bottom there, with all those C's and H's, that tries to illustrate a six-membered cyclic ring made up of the backbone is all carbon atoms. Each carbon has four things attached to it. In some cases, other carbon atoms, and at the very least, hydrogen atoms where there are no carbon bonds. But we assume that you know that. So the simplified structure at the lower right for cyclohexane uh, attempts to communicate the same thing. So just keep that in mind. There are a lot of extra atoms that are sort of left out of these structures for simplicity, and basically because it's just too hard to draw. Okay, so psychedelics. What are psychedelics? How do they work? Uh, Psychedelics are small molecules that are assumed to affect the responses of receptor proteins in nerve cells that are normally triggered by endogenous neurotransmitters. And although there may be more, these are the primary ones that we're interested in. Serotonin is probably the principal and required target of what we consider to be the hallucinogens and psychedelics. But also dopamine and epinephrine are very important in all of these responses. And we'll get into this a bit more when we talk about the different classes of psychedelics. But I want to draw attention to the structure. You'll see that in all three cases, we've got something that's very similar to, well, the two on the bottom are phenethylamines. The one on the top is an indole alkylamine, and we'll be getting into that in the third of these series where we talk about the tryptamine psychedelics. Okay, so I won't belabor the physiology of how nerves work, but this is a very simplified cartoon that kind of shows what we generally think of as the way that nerve information is passed around. So the uh, presynaptic neuron is basically the upstream source. So down through that chain going off into the background in the upper left, a nerve impulse comes down and uh, triggers the release of neurotransmitters from little packets inside the nerve that's the sending source. So there aren't actual connections, physical connections where the nerves touch one another. They communicate with, I've heard it referred to as soup and sparks. So there's an electrical impulse that comes in, but then that stimulates the release of neurotransmitters, which diffuse across a cleft between the two nerve cells, and then those neurotransmitters dock with receptor proteins on the receiving nerve and elicit responses that involve conformational change in the shape of those proteins. And then internal to the receiving cell, there are other proteins that start to move and trigger various biochemical processes, which create another impulse, which then moves on down the line. So we refer to that whole process as signaling, and the psychedelics alter that signaling, change it dramatically from what's kind of the normal pattern of behavior, and creates effects which are startling, sometimes delightful, sometimes terrifying, and this is the realm of study that we're going to address. So those receptors are proteins that dot the surface of the receiving nerve. Uh, this has now become something that we can manipulate with the advances of the Human Genome Project, sequencing of proteins, modeling of how proteins fold, which has kind of emerged in just the last 10 years with AlphaFold, and the development of artificial intelligence to predict the shape of proteins, we can now model how candidate drugs touch the surface of receptors, potentially alter their shape, potentially, well, we're not quite to the point of being able to predict how they alter signaling, but this gives you kind of an idea of the size of the molecules that the drugs are interacting with. And these structures that you see uh, illustrated are, in this case, LSD in a serotonin 2B receptor, a receptor that lives on your heart valve, um, and is a problem with some drugs, but we'll get to that perhaps in a little bit greater detail later. Okay, so this is kind of the broad spectrum of what we're going to be talking about. Now, uh, phenethylamines on the left side of this figure are by and large legitimate pharmaceuticals. A couple of those are drugs that are now controlled for fear of their abuse. But the second column are known antidepressants. Selegiline, bupropion, basically alter the rate at which neurotransmitters are repackaged. I didn't get into that, but after the neurotransmitters are released from vesicles, they have to diffuse back and be repackaged so that the process can repeat. Many antidepressants attempt to slow that process down so that there's more native neurotransmitter available to trigger nerve impulses and keep that process going. So, for instance, the selective serotonin reuptake inhibitors, the Prozacs of the world, focus on the repackaging of serotonin. Uh, the ones that I'm showing here mostly focus on the reuptake and packaging of the dopamine and epinephrine. So these are effective in treating depression. Bupropion has also been used in helping people quit smoking nicotine products. So on the far left are compounds that are more focused on the repackaging of dopamine. So amphetamine, propanolamine, phentermine, these tend to be stimulants, but they also tend to work on the appetite circuitry. So phentermine in particular is still used in weight control. On the far right, those two columns are some illustrative compounds that focus on the serotonin system. So the entactogens, MDA, MDMA, methylone, MBDB, are compounds that both cause the release of serotonin from vesicles and also compete with serotonin for reuptake. MDMA is particularly notable in causing a large flush of serotonin, also some epinephrine and dopamine, and it competes very strongly with serotonin for reuptake. So those of you who've had experience with it may recall that MDMA, particularly at higher doses, tends to cause kind of a washed out feeling maybe a day or two after the primary acute experience. This is because the serotonin is competed with so strongly that you really can't respond again. Methylone, although it doesn't produce the same degree of acute intoxication that MDMA does, also competes less. So methylone is sort of the weaker sister of MDMA. It causes much the same effect, but it's not as intense, and the after effects are not so strong. On the far right are some examples of, well, to kind of distinguish them between psychedelics that are entactogenic and hallucinogenic. this is an area it's kind of a semantic argument. Uh, some physiologists refer to the entactogens as an entirely different class. They shouldn't be called psychedelics. Some say, well, these are all psychedelics, and that the term psychedelic refers to uh, mind manifested. So the effects are primarily on perception, whether it's perception of the environment or perception of self. And certainly the entactogens have impact in those areas, but the entactogens don't tend to produce overt visual effects. So I like to call them all psychedelics, but refer to sort of subclasses that are either entactogenic or hallucinogenic, the latter having a strong visual component, either with the eyes open or the eyes closed. So I'd like to take a few minutes to just kind of sketch the history of how these things came to be known to Western science. Of course, indigenous peoples, both in the New World and the Old World, uh, knew of and used these compounds probably for thousands of years. Some of them may have, in fact, been central to religious practice. Certainly, that's the case in Central and South America. In other cases, their use may have been sort of proscribed. In Europe, for instance, the role of women who knew of plant medicines was uh, curtailed, discouraged, maybe feared in the Middle Ages, and so we have accounts of witches toiling over boiling cauldrons of natural products. Uh, Maybe they were treating themselves, maybe they were seeking enlightenment, um, but they didn't fit into society in the same way that the shamans of the New World did. So, in any event, talking about scientists, um, it turns out mescaline was really the first psychedelic to be studied in a systematic way. Um, there were pharmaceutical companies who became aware of it in the 1880s. Uh, Fairly large amounts of peyote were harvested and sent for study. But Arthur Hefter in 1897 is credited with carefully isolating mescaline from the large number of other related compounds that exist in peyote. There have been something like 55 different related compounds that have been identified from that plant over the years. So he isolated many of these from one another, sampled them personally until he was convinced that he had discovered the core activity, which was from mescaline itself. However, he didn't know the structure of it. That took another 22 years when Ernst Spath in Germany synthesized uh, mescaline, then proving its structure. In natural products chemistry, this is kind of the route, and in fact, in kind of all analytical chemistry, if you have an unknown, you can surmise what you think its structure might be. You can study it chromatographically or spectroscopically, but ultimately, to really prove that you know its structure, you must synthesize it and then compare your synthesized product with the one that you've isolated. So later, this gentleman, Gordon Alice, entered the field. Uh, he's credited with discovering the stimulant properties of amphetamine, although he was not the first to synthesize it. It was initially synthesized in Japan in the late 19th century, uh, but Alice resynthesized it himself, uh, uh, determined how to make the sulfate salt, and through personal experimentation discovered that it was a strong central nervous system stimulant. He also studied MDA, methylene dioxyamphetamine, uh, which was at that point an old compound, originally synthesized in Germany in 1919, but he resynthesized it and discovered its psychoactive properties and reported on that in 1930. Some have referred to that as the first synthetic psychedelic. There could be some argument about that, but he did go on to study MMDA, basically a 5-methoxy derivative of MDA, around the same time that our friend Alexander Shulgin prepared the same compound at Dow Chemical. We'll get to that a little bit later in this talk. They had planned to meet. Sasha was very impressed with Alice's forthright self-experimentation to determine the activity of these compounds. And they had intended to meet, but unfortunately, Alice, after a trip to Tahiti, um, uh, unexpectedly died. This is some irony. Alice, in his early career, had worked on the structure of insulin, but did not know that he was a diabetic. And apparently, the lack of that knowledge caused his death in 1962. So, um, Alexander Shulgin. Uh, Shulgin was a Berkeley product. He was born here in 1925. Uh, the son of an immigrant father from Russia who escaped the Bolshevik Revolution and immigrated to the United States through Alaska. His mom was English as a second language instructor in Berkeley. They met, and Sasha's father became her prime and favorite student. And soon their partnership produced this gentleman. Uh, Sasha was a very bright kid. Give you some idea. He was both an author of poetry starting at, I think, about age 7. He got a full ride scholarship to Harvard at age 15. Um, Attended for about a year and a half, but never felt that he really fit in. Uh, Basically called himself a troublemaker. And, a kid of that age, amongst the sons and daughters of uh, industrial magnates and powerful politicians, he just didn't feel like he fit in. So he left Harvard, joined the Navy, and spent the last 2 years of World War II working on a destroyer tender in the North Atlantic. Came back to Berkeley, breezed through organic chemistry. He had one book apparently when he was on board ship, um, about a 3-inch thick organic chemistry text, which he memorized. So when he got to Berkeley, uh, really classes were not a challenge to him. One of his profs, after their first organic midterm, said, "Shulgin, come over here. You really don't have to take those exams." Sasha said, "Well, why not?" He goes, "Well, the class average for this one was about what we normally expect. It was 40%. You got 100%. So clearly you know this material. If you'd like to take the exams for practice, you're more than welcome, but you really don't have to." So anyway, he completed his bachelor's doctorate in biochemistry in 1955. Uh, Worked for a few local companies, but ended up at Dow Chemical in Walnut Creek, California, by approximately 1957, and was exposed to mescaline probably around 1959. And it was a profound experience that triggered his interest and fascination and led to a nearly 50-year journey into the study of the chemistry of related compounds. Now, more recently, starting in the early 1970s, the situation changed. Prior to that point, there had not really been a stigma preventing scientists from working on psychedelics. But with change in mores and gradual conservatism, concern about the absorption of psychedelics into counterculture, uh, passage of the Controlled Substances Act here in the United States in 1970, the situation changed very drastically. Uh, Pretty quickly after the CSA was passed, the concept of a war on drugs was initiated. And around that time, formal research into psychedelics, their mechanism of action, was greatly curtailed, almost eliminated. During that whole period, though, there were at least two gentlemen who were able to maintain funding for their research. David Nichols at Purdue University and Richard Glennon at Virginia Commonwealth uh, kind of competed with one another in a way, both synthesizing new compounds and determining how they interacted at a molecular level with what became known as the serotonin receptor families. Keep in mind that uh, during the period of time when Shulgin was working on development of new compounds, the concept of receptors in the nervous system was basically just being born. So the extended work of Nichols and Glennon from the early 1970s through the 2000s really laid the groundwork for what we know, what we understand today about how these small molecules work in the brain and how we might be able to design new ones to directly address the most intractable problems of mental health.
Hey, Paul,
Yeah,
why were David and Richard able to continue their experiments? What made their research able to continue throughout the war on drugs?
well, impeccable intellectual product. Both of them started right around the time that things were starting to shut down. But they had funding initially. They wrote great grant proposals and defended their work at the very highest level of scientific rigor. So that's an inspiration to anyone trying to get into this field now. Do your homework and write it up really well so that you can convince even the most ideological detractors. Put it that way.
Thank you.
You bet. So now let's start looking at molecules. So this whole story of the phenethylamines really starts with mescaline. Uh, as I said, structure worked out in the 1920s. Uh, Mescaline is a lovely compound which inspired intellectuals, writers who were curious about it in the years before the controls started to shut down. Aldous Huxley's brilliant writing of The Doors of Perception and Heaven and Hell clearly inspired a lot of people to explore this compound and led ultimately to Sasha's experience with purified mescaline and his wife Anne's discovery of psychedelia with peyote experience, uh, which took place at about the same time, but it was on the order of almost 20 years before they met one another. So uh, a lot of the early synthetic efforts focused on modest modifications of the mescaline molecule. The two compounds here were some of the first that were synthesized, kind of riffing off the scaffold of mescaline. TMA was synthesized in 1947. Took a couple of years before a report came out about its activity, but it was claimed to be about twice as potent as mescaline. Shulgin took it and uh, remarked that it was qualitatively distinct from mescaline. He remarked on its anti-social character, uh, causing paranoid delusions and hostility. Uh, and this kind of blew a hole in one of the kind of predominant dogmas of the time in the very early 50s, which was that the known psychedelics, mescaline, LSD, and psilocybin, all produced the same effect They only differed in potency and duration. But Sasha's experience with TMA clearly showed that these had different effects. They probably interacted with the biology of the brain in different ways, and this kind of triggered him into a medicinal chemistry exploration that lasted for the balance of his life. Now, finding that TMA was about twice as potent as mescaline with just the addition of that stick pointing down at the alpha carbon is another methyl group. So uh, uh, with that in mind, he synthesized a whole series of lengthened chains at that location. But unfortunately, even with the first one, which is in the lower left there, AEM, alpha ethyl mescaline, uh, this was completely inactive. So the effort to synthesize that family of chain um, extensions was useless and abandoned.
When you say twice the potency with TMA, do you mean intensity or like half-life?
Uh, well, in other words, in order to reach the same level of intensity, it would take half the material. And
Heard that. Thank you, sir.
yeah, and the duration, I believe, is approximately the same. So we'll get into some duration effects actually starting now. Uh, so Shulgin started to perform other modifications. He altered at all the locations of known uh, functional groups. So it looked like working on the side chain was unproductive. So he started to modify the ring substitutions, found fairly early on that modifying in the 3 and the 5 position, and you can see the numbering convention that we use in the upper left there. The 3 and 5 position modifications really either curtailed activity to a great degree or eliminated it completely. But modifications at the 4 position were fruitful. So in some cases, the effects were prolonged, with which you can see with CPM, uh, both an increase in potency and an increase of duration of about 50%. So these were all, encouraging, but there were still more answers to be found. Now, fortunately, one of the efforts that he undertook pretty early on was to modify the positions around the ring. So working off TMA itself, which was the unmodified 3,4,5 trimethoxy configuration. The first compound in this next series that he prepared was what he called TMA2. So the side chain is unchanged from TMA. The one change on the ring is that one of the methoxys is moved from the 3 position to the 2 position. Well, this produced about a 10-fold increase in potency. Didn't change the duration all that much, but it preserved the desirable uh, mystical, colorful, beneficial psychological effects of mescaline. So this is a very significant discovery. It turns out that doing further modifications, if you left the 2,5-dimethoxy core motif and just modified what was on the 4 position, you were almost guaranteed to have a new psychedelic. So, and kind of parenthetically, the 2,6 configuration that you see in the lower right from TMA6 is also a treasure trove of structures that if you keep the 2,6 dimethoxy combination and have something hydrophobic at the 4 position, you're also guaranteed to have a new psychedelic. Those have been less explored, but chemists in the future may want to take a look at some of those. Interestingly enough, though, the other positional isomers that you see in the center there were also prepared and assayed, and basically their activity was highly reduced or absent. In some cases, as with TMA5, there may have been activity, but it was more in the stimulant ballpark as opposed to psychedelic. So the 2,5-dimethoxy configuration was something that Sasha explored extensively. And there were a large number of compounds that varied very broadly in potency and duration. Some of those are illustrated here. DOM was also known as STP for a short time in the 1960s. It was introduced right around the time that Sasha was leaving Dow Chemical. He had been approached by Stanley Osley and Tim Scully, who were young clandestine chemist entrepreneurs in the Bay Area who were searching for LSD substitutes. Since that compound had been made illegal in California. Yes, I see a steal your face showing up there. So Owsley and Scully approached Sasha. They knew of his work. They were wondering if there were any compounds that he could help them with that might provide the community the psychedelics they wanted and needed. And Sasha was gracious enough to apparently give them a 50-gram sample of DOM. That was packaged up in tablets of either 10 or 20 milligrams and handed out for free at the Summer Solstice Festival at the beginning of June in 1967 in Golden Gate Park in San Francisco. Approximately 2,000 tabs were given out. People were told that it was an LSD substitute, and they were not also educated in the fact that DOM is potentially very long, almost 50% longer than LSD, but also has a long latent period. The interval between the time that it's consumed and the first effects start to be felt can be on the order of an hour or two. So people being used to LSD effects being felt within as little as 20 to 30 minutes, probably in some cases thought, oh, well, I must not have gotten enough. So if you can imagine people consuming 10, 20 milligrams already at the high end of an effective dose and doubling or tripling up on that, they were probably in for quite a ride. Of the few thousand tablets that were given out, there were people that were sufficiently distressed by where their mental state was that they were reported for medical assistance. And of course, the local hospitals didn't really know what they were dealing with. This was a new drug. They had no analytical background, had not been released, had not been published. And so it gained kind of a dark reputation. With that in mind, it still was a very effective serotonin agonist. I should have pointed out that the entactogens are generally referred to as serotonin releasers. They tend to promote the release from the encapsulating vesicles. The true psychedelics are agonists. They actually bind to the serotonin receptors and turn them on, activate them. So all of these compounds are serotonin agonists. DOM has been used as a training compound in animal studies by both Glennon and David Nichols very successfully over the years, and used to distinguish entactogenic effects, from true serotonergic psychedelic effects, and stimulant effects. We can get into that a little bit later. In any event, most of these DO series tend to be both quite potent and also quite long. If the dose is pushed in humans, the experiences tend to be prolonged even further. So they're very wearing. If you can imagine, 30 hours on a strong psychedelic like DOB can be, a little taxing.
Paul, just very briefly, hi, by the way. Uh, did the study of duration change after ECL2 was discovered in like the early 2000s? Did that shift how people approach duration of efficacy?
ECL2, inform me on what that is.
It's the lid that clamps down over the receptor that actually holds
Okay,
the
sure.
like a binding agent.
Well, all of these durations are emerged from Shulgin's work back in the 60s. So that degree of understanding of the like molecular conformation of how these things are, some of them like the lysergamides are kind of trapped in the receptor, didn't emerge until the 2000s. So it's possible that some of these may work in the same way at the receptor level, but to the best of my knowledge, most of these long-acting amphetamine psychedelics have not been studied with those modern methods. The cryo-electron microscopy and the techniques that were used to generate that picture of how the lysergamides are trapped in the serotonin receptors. Does that answer your question?
Totally, thank you.
Okay. All right. Well, in any event, so realizing that there was probably some room for improvement in how these things could be used, Sasha turned his attention to the 2-carbon versions of many of the compounds that he produced while still at Dow Chemical in the 1960s. So in the 1970s, when he decamped back to the lab here in Lafayette, he produced these 2C compounds. So the side chain is just lacking that alpha methyl group, so it's a 2-carbon chain. And I presented these kind of laid right on top of the sort of DO series prototypes. And as you can see, the durations are cut way down. And the potency is probably also about halved. So more material is required, but basically the latency period is also reduced. So these things are much more tractable. And some of these are some of these have been experimented with as psychotherapeutic substances. And we're very hopeful that as we figure out how to use these in a clinical setting, that some interest may shift over to these once again. But this is not to say that in all that effort, there were not some compounds that made life a little challenging. So we thank Matt Baggett, our friend, for kind of analyzing the extent of compounds reported in PCAL. Of the 107 positively active compounds, there are probably another 75 or so that were never tasted. Many were their active level was not ever determined. There are a few that were toxic, and there are some that have idiosyncratic uses or idiosyncratic effects. 5-tom on the left side, in one case produced basically a catatonic reaction where the subject became like what's the Bugs Bunny phrase? Non compos mentis. during the plateau of the experience, this gentleman was basically unable to walk unassisted, unable to speak, and all those effects lifted at the as the effects of the drug wore off. But clearly there had to be a great deal of care in experimenting with these things, where the only experimental animal was the researcher himself. Now, this situation has changed very drastically. Up until about the mid 1980s, there really was not a strong stigma about self-administration of experimental drugs, but that began to shift. Uh, Social pressures started to emerge, and the scientific publishers started to hesitate with publication of research papers that included description of human effects. At the same time, the molecular technologies that are now commonplace started to emerge. So there was and in addition, there of course were also animal methods that had not existed before that allowed identification of psychedelic effects and distinguishment of those from stimulant effects and even entactogenic effects. So since the mid 1980s, self-administration has been frowned upon, avoided. That situation may be gradually changing, but hasn't completely happened yet. One last group of compounds that I'll touch on before we close are these entactogens. Shulgin actually got started with these back in the early 60s. Both Alice and Shulgin were aware that prison inmates would consume nutmeg as a drug of recreational drug, shall we say. Alice had done studies with allylbenzene and discovered that if you feed it to liver slices from mice, the liver actually adds an ammonia group and creates small amounts of amphetamine. So the question was, can compounds like myristicin and safrole that exist in nutmeg and other plant sources be converted in the body to drug-like molecules? So they both produced MMDA at around the same time in 1962. The MMDA series includes several positional isomers. MMDA itself was experimented to a degree by Claudio Naranjo here in the Bay Area for psychiatric use and found to be positive. And of course, now there's an explosion of interest in MDMA for exactly that kind of application. There are quite a number of other related compounds, and these are all releasers. Amphetamine, primarily a releaser of dopamine, to a lesser degree epinephrine. And MMDA and MDMA are both strong serotonin releasers. So finally, at the end here, I'm going to give you a couple of examples of how these things are made. This is, in fact, a chemistry lecture. MDMA is often produced from safrole as a starting material. It needs to initially be oxidized. I'm illustrating it here with benzoquinone and palladium chloride catalyst to produce the ketone methylene dioxy-2-propanone. And then that goes through what's called a reductive amination with sodium borohydride and methylamine or nitromethane to produce MDMA. The latter method with borohydride was one that was published by Nair et al., the group that were producing MDMA for the MAPS effort. This is a reaction that's common to many of the structures that we've been talking about. Once you have the ring combination that you want for your final design, you need to add that side chain. And that's often done with what's called a Henry reaction. So the you start with an aldehyde and react that with nitromethane or nitroethane uh, as the core of the carbon nitrogen bonds. And in this case, the butylamine it attaches itself temporarily in the third step and is then broken off, forming a nitroethene. That's reduced with lithium aluminum hydride to form 2CH at the lower right. And then that's reacted with elemental bromine and glacial acetic acid to produce, in this case, 2CB. Lithium aluminum hydride is a fabulous compound for doing those reductions, but it's pyrophoric, which is to say that in contact with moist air, with water, it can burst into flame. The reactions are usually done in flammable solvents. So as you could imagine, it's a little hairy particularly for beginners. So recently there's been development of a new alternative approach that's kind of two-step but done in one pot, using first borohydride to reduce the alkene to an alkane you see in the center there. And then with the addition of copper chloride and water, the nitro group is reduced to the amine. Now, for a number of molecules, there are more steps. This one actually shows you what you have to go through to get the ring substitution pattern that you want for, in this case, the final thioether compound 2CT16. Since we're kind of at the hour, I'm not going to go through the mechanisms of this. This is just to illustrate that you have to start with the ring substitutions and then add the side chains that complete the molecule. And I should say that for those who don't have access to full organic chemistry labs, there are lovely methods now for extracting quite pure crystals from, for instance, mescaline containing cactus, which gives access to those materials and experiences for those who don't work in organic labs. For those who do, I've got some quick safety notes. All these intermediates and reagents are potentially hazardous or toxic. You really need to get your training in order to attempt any of these. Learn how to protect yourself with both the lab that you're working in and also personal protective equipment. Handle your waste in an appropriate way. Never pour chemical waste into sewers or surface waters. And talk to us older chemists. We're happy to help, but do pay attention. Sometimes people get ahead of themselves. And are there any questions I can attempt to answer?
I have
Well,
some in the chat. So I've been receiving some directly. Thank you so much, Paul. And I know we're a little bit past, and as I said, I will be sending out this recording to everyone tomorrow if you have to jump. And I also just wanted to share that we have events coming up, and I'll drop the chat for anybody that wants to join us. The other dates for this, for part 2 and 3, will be Wednesday, May 27th and Wednesday, November 18th. And as you all know, the Shulgin Foundation is a 501(c)(3) nonprofit organization, and we really rely on donations to continue supporting the legacy and rebuilding the Shulgin farm. So if you feel like supporting us, I will drop that donation link in chat in case you want to support us further. And in the meantime, Paul, we had a question from Bob asking, some companies are working to improve the therapeutic profile and reduce toxicity in MDMA. What do you think their chances are, and what mechanisms would make this possible?
I think the chances are pretty good, and there are a variety of routes. You pointed out that there are two organizations represented here today. We've got the Shulgin Foundation. I'm spearheading the Alexander Shulgin Research Institute, which is a for-profit drug discovery unit, we have programs looking at a variety of different uh, families of compounds, and MDMA-like compounds are in there. You can look at, for instance, the reuptake inhibition. Methylone, which I illustrated, was an attempt by Sasha and his associate Peyton Jacob to develop a less neurotoxic version of MDMA, and they were partially successful. So in any way that you can modify the absorption, metabolism, distribution, excretion of a molecule, you've got a handle on both direct acute effects and after effects. So we've done that by adding stable hydrogen isotopes in parts of the molecule. The deuterium carbon bonds are harder to break, so that slows metabolism. So there are a variety of strategies, and there are also structural modifications. Matt Baggett has a company, Entactogen, who are working on closely related molecules to MDMA that in that methylene dioxy kind of side five-membered ring have only one oxygen. And those tend to be less neurotoxic and still MDMA-like in effect. So I hope that gives an answer.
Amazing. Well, I'm going to read off one more question since I know we're a bit over. And we had a few people show interest in this one, which is, how do I get into working on this frontier of science? They're a trained chemist, and this is what they want to apply themselves to a career. And after some powerful psychedelic experiences that have healed them so much, they want to work in this field.
Well, if you've already got some training under your belt, there are kind of two routes. You can go for more graduate education. You know, get your degree in pharmacology, toxicology, organic chemistry. Uh, Going all the way through to the PhD can be very daunting when you're, sort of looking at how much work and grief is involved in getting there. But at the back end, it can give you a tremendous degree of freedom in terms of what, how you fashion your career after that point. But it's not the only way. If you've got, at least a master's degree, you could offer yourself as a potential employee at any of the numerous companies that are developing new compounds. Be aware that we're in a transitional phase right now. A lot of small companies find it economically challenging to support having organic chemistry labs, and they would prefer to outsource all of the bench chemistry to Chinese or Indian laboratories, and they are hungry for work and very competitive in terms of price and speed. So the higher your educational degree, the more you have a chance of actually directing that work, maybe doing some pilot work of your own, but then having a better experiential base to advise companies in terms of what avenues are going to be fruitful and which aren't. But just more education, more training. It's unavoidable.
Awesome. Well, there were a lot of other questions, and I just want to thank everyone for sending them. You all will receive this recording. And yeah, Paul, thank you so much for doing this. And everyone else, thank you so much. I am our programs director, Stacy, and I'll drop my email in case you have any further questions that we can help you with. Otherwise, please come join us, and the other sessions are in chat. And we will catch you next time. Thank you all so, so much.
Well, you're very welcome. Thank you all for coming.
Awesome. Thanks.
Take
Thank you.
care.
Thanks, Paul.
Thank you. Appreciate you.
Bye, everyone.
Thank you so much.
Thank you, Paul.
Thank
Thank you
you,
so
Paul.
much.
Thank you, Paul.
Thank you for your time.